the purpose of this course is to introduce you to engineering through the study of structural engineering, perhaps the oldest part of engineering and my discipline. And I've entitled my talk, which introduces you to this discipline, In Search of Elegance. The formal definition of this discipline is that it's the art and science of designing and making structures with economy and elegance so they can safely resist the forces to which they may be subjected. Economical, safe, but also elegant. These ideas are very old. The Roman engineer, architect Vitruvius, in a book he wrote in about 30 BC, described the requirements for structures as being that structures should have the qualities of firmitas, utilitas, venustas. That is, they should be firm, strong, they should be useful, and lastly, they should be beautiful. Venustas, the goddess of love. Now, Vitruvius wrote this little book, addressed it to a young man who was about to become the first Roman Emperor, Augustus. And this young man, at the age of 19, had inherited from his great uncle, Julius Caesar, the right to rule Rome. But first he had to win a long civil war. And having won that, he began to reconstruct Rome. And that's why Vitruvius wrote him this book. Because, as Vitruvius said in the preface, I have drawn up definite rules to enable you to have personal knowledge of the quality of buildings. For in the following I have disclosed to you all the principles of the art. This book was written so the emperor would understand the details. The Romans had a funny idea. This idea was that the person in charge should understand the details. The fact that structures should be useful and strong and beautiful applied not just to temples, but also to utilitarian structures like this aqueduct, the Pont de Garde, which carries drinking water from Uzès to the big town of Nîmes, a distance of 50 kilometers. And over that distance, the water drops just 17 meters. So it's a magnificent feat of engineering to bring the water that distance with that smaller drop. And as they go over the valley of the Garde, they needed this big structure to carry the aqueduct at the right level. And this aqueduct was one of the many built by Marcus Agrippa, Augustus's best friend, contemporary, son-in-law, and named heir, and the person who transformed Roman engineering in these years. Here's how the Romans felt about these structures. These are the words written by Sextus Julius Frontinus, curator aquarum of Rome, beginning in AD 97. Will anybody compare the idol pyramids, or those other useless though much renowned works of the Greeks, with these aqueducts, with these many indispensable structures? There speaks an engineer. He's not interested in non-useful structures. These structures are indispensable. They happen also to be beautiful. Now, Frontinus had had one or two other administrative tasks before he took over this job. He had been governor of Britain and was consul of Rome 3 times. Was one of the most powerful and important men in the empire, and he was in charge of the aqueducts. About the time Frontinus was writing those words, this bridge was being built in Spain. It's the Puente de Alcantara. It's across the Tagus River, close to the border between Spain and Portugal, in a region called the Extremadura. And this hard, tough region was settled by Caesar's legions. Augustus put them there. And the descendants of these hard, tough men built this hard, tough bridge, and built it of granite, the strongest stone, and the hardest stone to work with, the most difficult stone to work with. And when they'd finished, they knew they'd done something rather special. And at the end of the bridge, just out of sight over on this left side, the builder of the bridge built a small temple, roadside shrine. And over that temple he put a plaque and he said, "Please pray for the bridge," and that's obviously worked. And secondly, perhaps you're interested to know who built this bridge. And he says, "I, Caius Julius Caesar, famous for my art, leave a bridge to stand forever in the centuries of the world. I'm bloody good at what I do, and what I've just built is going to last forever." And so far it's lasted 19 centuries, so it's not doing too bad. There's a car passing over it there in this photograph I took a couple of years ago. Those two structures we just looked at, the Pont de Garde and the Alcantara, both use semicircular arches. That is an arch which is half a circle. So it goes up a radius and its span is a diameter twice as much. When built in a steep valley, that makes sense, but if you are in flat country, the bridge is too high. And so the Romans knew that and were quite capable of building what we call a segmental arch, which is a segment of a circle, not the full half circle. And this is a segmental arch bridge at Ciudad Rodrigo, a few hundred kilometers north of the Alcantara, built about the same time. And this bridge has a rise of 1/3 of the span and is a rather elegant bridge. Beautiful, I think. This is the longest span stone arch bridge that the Romans built. It's the Pont Saint-Martin, and it's also a segmental arch. Again, its rise is 1/3 of the span, but this time the span is 120 Roman feet, which is about 116 English feet. That was the longest they ever tried, and I think that was the case because there is evidence in this bridge that it nearly collapsed when the forms were removed. I don't know if you can see it, but off on the upper left there, that isn't a very smooth line. It sort of curves down, and you can perhaps see the iron clamps that they have put in to hold the stones in place. So this bridge nearly collapsed, and they moved back from that and never tried going over 100 feet thereafter. Not in bridges anyway. But in this remarkable building, they went to 150 feet. This is Hadrian's Pantheon. Hadrian, I believe, was the greatest of the Roman emperors. And certainly under his rule, Rome had its best time, its best standard of living. And Hadrian was called the builder. And all over the empire he built fantastic structures. And in Rome he built the greatest of all Roman structures, this building. It's a dome made of concrete. The Romans knew about concrete and were masters at using it. And this building has a span, the roof has a span of 150 Roman feet. And the height is 150 feet. So a perfect sphere could be placed inside the building and would just touch the floor and go to the roof. The light comes in through the oculus, 30 feet in diameter. Imagine walking into this building. If you go to Rome, do it. It's a fantastic building. But it's designed to impress from the inside, not the out. When you walk inside, you see something that's 15 stories high and 150 feet in span. That was the biggest span until a building was built in about 1880 that had a slightly bigger span. So for more than 1,700 years, this was the biggest roof in the world. This is what it looks like inside. It's awe-inspiring, and it's meant to be. People have commented on it. For example, Byron said, simple, erect, severe, austere, sublime, shrine of all saints, temple of all gods, spared and blessed by time. And Shelley said, it is, as it were, the visible image of the universe. If you lie on your back and look straight up, this is what it looks like. And it's a temple to all the gods, the pantheon. And for the Romans, the gods were the planets: Mercury, Venus, Mars, Jupiter, Saturn, the 5 planets. And if you count the rings, you'll see 5. 1, 2, 3, 4, 5, circling around the sun. The visible image of the universe. Now, after the fall of Rome, much of Roman technology was lost, but elegant structures were still built. And this is a Viking ship. It's the Gogstad ship. It was dug out of the mud in Norway about 70 years ago. It was built in 850 AD out of oak planks held together by iron rivets. The oak planks have been steamed to bend them into the right shape. It has been called the most beautiful object ever made by man. But it wasn't made as a work of art. It was made as a warship. It was a terrible weapon. It terrified Western Europe. A prayer of the time was, from the fury of the Norsemen, O God, protect me. They could reach anywhere that was accessible from a decent river, because these had a very shallow draft. This particular vessel had 32 oars, but the really big ones had 70 ferocious Scandinavians coming out of these. The Norse sagas talk about them, and I'd like to read you a few lines from one of these sagas about King Harald. One Saturday, King Harald hauled down the long deck awnings, and Trondheim women proudly watched the ship glide past. The young sea king was steering his new ship down the Nid, while battle-hungry warriors dipped oars into the water. Norwegian arms are driving this iron-studded dragon down the storm-tossed river like an eagle with wings flapping. Can you visualize that? As I said, they went almost everywhere. And including those places is Canada. They came to Canada. And they landed in the far north of Newfoundland at a point called Lancer Meadows, shown here. And as you see, there were people waiting to greet them and a helicopter in the sky. This was 1000 AD, but actually this photo was taken 1,000 years later when it was reenacted with a group of replica Viking ships who sailed out from Norway and followed their route. They smelted the first iron in the Americas there, and they survived there 3 years before packing up and going home. And if they had have lasted longer, my lecture today would be given in Norwegian. The rest of Europe worked hard at dealing with the Vikings, and what they eventually did was convert them to Christianity. And after that came a period of great prosperity in northwestern Europe. And they gave thanks by building these magnificent cathedrals. This one at Amiens was finished in about 1280 AD. It's the tallest cathedral in France. And it's just a meter higher than the Pantheon. But it's much narrower, so it looks much higher. And instead of the light coming in from that single oculus, the light floods in from those magnificent stained glass windows. At about the same time, a number of medieval bridges were built, often by monks, or religious orders were involved quite often. But strangely enough, these bridges often are called the Devil's Bridge, because later people couldn't understand how this apparently magic structure had been built, because it required great skill and knowledge to build an arch like this. This is the Magdalena Bridge, which was on the Pilgrim Road to Rome in Tuscany. It's near the town of Lucca, built in the first years of the 1300s. A century later, the Renaissance began, and it began in this city, Florence, which began to compare itself to ancient Athens and Rome. And we see here some workmen building a bridge across the Arno. And each spring the Arno flooded, and they had to build defenses for the city to protect them against the flood. And often the bridges were wiped away by the flood, so they had to rebuild them. Here they're driving piles, using technology that the Romans used. In the background you see one of the achievements of Florence of that century, Filippo Brunelleschi's dome, which had exactly the same span as the Pantheon, but is built much higher in the air. The people of that time looked back upon the ancient learning, and they tried to understand how the Romans had done it. And one of the things that happened was in a monastery at St. Gallen in Switzerland, they found a good copy of Vitruvius's manuscript. It had been copied many times, but it was much better than any other they had. Unfortunately, the figures had been lost. And so a young man in Florence, reading the text, drew his own version of the figure that obviously should have accompanied it. And this is from a part of Vitruvius which tells Augustus that the different parts of a building should be in proportion, one to the other, as the parts of the human body are. And so he says, for example, that the hand from the bottom of the palm to the tips of the finger is exactly 1/10 of the height. And the distance from the bottom of your chin to the bottom of your hair is exactly the same. So to put your hand here, it should fit. And Leonardo drew a figure which had all of these proportions that Vitruvius gives. Leonardo was in his late 20s when he drew this, and it's believed he used himself as the model. Towards the end of life, he drew another self-portrait, and I've used that to accompany a note he made in his notebooks many years before. It was a very modern statement because he not only studied ancient writings like Vitruvius, he also did physical experiments. And he says, in the examination of physical problems, I begin by making a few experiments because it's my desire to state the problem after I've had the experience of it. We must commence with experience and strive by means of it to discover truth. That's the heart of science. And you could make an argument that Leonardo was the first scientist, the first modern scientist. These are some of the experiments he did. He made his living as an engineer. He was a civil engineer. And amongst other things, he had designs to save Florence against the flooding of the Arno. Here he's looking at arches, and he's asking the question, what is the force required to prevent each of these arches from giving way? When we push upon an arch, what happens is it tends to go down. So if I push, the arch goes out. And to stop the arch going out, I must hold it here. And that's called the abutment force. And unless you hold it there, the arch collapses. And Leonardo asks, what's the force? How do I calculate the force? And he does experiments. And he sees that a very flat arch requires more force than a high arch. And he suggests it's got something to do with this angle. And he's on the right path there. Towards the end of his life, he wrote a proposal to Sultan Selim of the Ottoman Empire, who was desirous of building a bridge at Pera in Constantinople across the Golden Horn. And here in his notes he says the bridge of Pera at Constantinople, 40 brachia wide, which is about 60 feet, 70 brachia high above the water, 600 brachia long, that is 400 over sea and 200 on land, thus making its own abutments. He's proposing an arch whose rise is 1/3 of its span, and he's proposing an arch with a span of 600 feet. And the Romans had difficulty with 120. And so it's not surprising that Sultan Selim decided to give this proposal a pass, and he built a floating bridge. But about 3 years ago, some engineers in Norway had this bridge built as a highway overpass, a small model of it, and it worked very well. Leonardo's lines are correct. Sultan Selim's successor was Suleiman the Magnificent, the greatest of the Ottoman leaders. And he had a court architect called Sinan, a master builder. And Sinan had a school within the palace to teach people building. One of his pupils became an engineer, and his name was Hayrattin. And Hayrattin built this bridge at Mostar in Bosnia. And Mostar means bridge, just the way Alcantara means bridge. And this bridge has been called the most beautiful and the boldest of all stone bridges. It's bold not because it has a big span, because it's very slender. The thickness of the arch is only 1/37 of the span, whereas for a typical Roman bridge it would be about 1/15 or 1/20 of the span. It's a testament to the virtuosity of Turkish engineering at that time. About the time that bridge was being finished, an Italian almost as brilliant as Leonardo, called Galileo, was born. And near the end of his life, he was arrested by the Inquisition and was lucky to escape with just being subjected to house arrest. He had committed 2 grievous sins. One was to say that the earth revolved around the sun, but the second, and perhaps more important, was to make fun of the Pope. Under house arrest, he was not supposed to write any technical things because those writings had made fun of the ideas the Pope had about how the universe worked. But he disobeyed those orders, and he wrote a book in secret and smuggled it out, and it was published in Holland. This book was called Dialogues Concerning Two New Sciences. And Galileo said he thought this was the greatest work of his life. And those 2 new sciences, the first of those 2 new sciences, was the resistance which solid bodies offer to fracture. And he said, we suppose as a basis that we know the force required to pull apart a material under straight pull. And from that, we build many useful results. So if I know that, can I work out what force it takes to break it this way? This is what's called bending. And it's much easier to break it that way. I can't break the stick this way. The stick would take 8 times my weight before it breaks. But this way, I can break it with my finger and thumb if I really push. Certainly easily with my hand. And so Galileo said, what happens if I put a piece of timber and I attach it strongly to the wall, and at the other end I hang a very large weight? When will it break? And that's the issue of bending the stick. And he nearly got it right, but he made some mistakes. And the person who was the first to get it right was someone who was just 3 years old when Galileo died. He was Robert Hooke. Hooke has been called probably the most inventive man who ever lived. He's also been called the Leonardo of London. He was employed as the curator of experiments by the Royal Society, and he really turned the Royal Society into a modern scientific organization. His job was every week at the weekly meetings to produce 2 or 3 original experiments. Original. So all you have to do is come up with 2 or 3 inventions every week and then demonstrate them to the members. No problem, right? And he did everything. I mean, he just went all over the place. So if you read Hooke's notes and what he did, then you'll find fairly clear statements of the theory of evolution, all sorts of things about geology, fossils, cells, all of science. And in a paper in 1678, he examined the springiness of materials, what he called the true theory of elasticity. And he tried to understand why a bow works and springs the arrow, how the energy is stored. And he talked about the particles which get, when you bend something, which get pushed closer together, in this case on the bottom side, and stretched further apart on the top. And how these little particles typically vibrate back and forth, perhaps 1,000,000 times a second, he thought. And as you push them closer, they bang into each other and want to go back. And when you pull them apart, they don't hit so often. So they wish to head back. There is a stable position. And if you disturb them from that stable position, they try to go back. They act like springs. And he has it right. This is still the basis of our modern engineering theory of beams. Hooke was deeply involved in rebuilding London after the Great Fire, and this is one of his few surviving buildings. It's his monument to the Great Fire, built of Portland stone and 202 feet high. You can go up inside it, and there's a viewing platform on the top. His greatest friend was Christopher Wren, and together they were involved in many of the major structures, to rebuild many of the structures in London, the most significant being St. Paul's Cathedral. And so Hooke turned his inventive genius to the question that Leonardo had asked: what is the true abutment force? And Hooke published his theory with this introduction: this is the true mathematical and mechanical form of all manner of arches for building, with the true abutment force necessary for each of them, a problem which no architectural writer has ever yet attempted, much less performed. Here's the correct form, and here's the correct magnitude of the abutment force. And here's his theory. But he'd got rather sick of people pinching his ideas. He would give these talks every week, and many of the ideas were ones he just came up with on Monday and the talks on Friday. And then other people would go away and work on his ideas and publish it and say, well, I knew that already. You know, I didn't get it from you. It was my idea. You just had the same idea at the same time. So how do you establish priority? So what he did was publish 10 of his inventions in the form of anagrams like this, just the letters in alphabetical order. And he described each one. What I just read you is what that theory is stated here. He said, here's my theory for the true theory of arches. Now, if you know the true theory of arches, you tell me what it is. But if you don't claim later that you did, right? And some years later, he published the solution. Here it is. These are those letters just rearranged. These letters in alphabetical order make that. And this is the English translation. As hangs a flexible cable, so inverted stand the touching pieces of an arch. If you want to know the right shape of an arch, hang weights on a cable and turn it upside down. Because a cable can only take tension, and an arch should only take compression. The arch is not good at resisting bending, and the cable can't resist it at all. And it's brilliant. Hooke kept a diary, and his diary for June the 5th, 1675 says, at Sir Christopher's, he was making use of my principle about arches and altering his model by it. here's Wren's great building, St. Paul's. And the dome is the brick cone, which is inside, shaded there, and that's holding up that, what's called the lantern, which is 800 tons of stone on the top, which really holds the top down against wind force. Designed by Hooke's theory. And, by the way, Hooke supervised the construction along with Wren. As that cathedral was being finished, a lighthouse was being built on a rock off the south coast of England called the Eddystone Rock. And that first one blew down in a storm, and the second one burnt down, and this is the third and the most famous of the Eddystone lights. It was built by John Smeaton, who was the first to call himself a civil engineer. And he tried to rediscover this Roman cement that the Romans were so effective at using. And so this is the first structure since Roman times to use concrete. A little later than that, in 1792, this bridge in Paris, the Pont de la Concorde, built by Rudolph Perronet, was completed in the middle of the French Revolution. In fact, some stones from the Bastille were used in the finishing of the bridge. Perronet was 82 years old when he finished this, and he had been the first director of the École de Ponts et Chaussées, the first engineering school in the world, anything like this one that you've just joined. And this is a very daring bridge because the arches are so flat and the piers are so narrow. And Perronet's younger colleagues were very worried that this bridge would collapse when the forms were taken down. So it was quite a dramatic event when the forms came down and the bridge stood. Actually, Perronet had cheated because the night before he went out and had some of the workmen lower the forms a little to check that it was okay. Then they had the big public event of lowering them, and he'd already knew it was okay. England, rather than a real revolution, had an industrial revolution. But nevertheless, by the end of the 18th century, huge changes had occurred, and England was now very wealthy and wished to improve access to the Port of London by replacing the old London Bridge, the one that little kids sing about in the song of London Bridge is Falling Down, with a modern bridge which would allow ships to get up into the Port of London. And the Committee of Parliament, who was to choose the winner of this competition, got this audacious design from a young Scottish stonemason who wasn't even an engineer. And this was for a 600-foot arch straight across the Thames, whereas they had expected one with perhaps 4 arches across the Thames. And no one had ever built an arch this long, 600 feet. It's the same as Leonardo's. They appointed a committee of professors, the Professor of Mathematics of Oxford, the Professor of Mathematics of Cambridge, and the Professor of Mathematics at Edinburgh to study Telford's design. And these 3 professors couldn't agree about anything. And so the bridge was not built. And Telford, for the rest of his life, believed that professors knew nothing about engineering. And when he became the first president of the Institution of Engineers, that belief permeated the English-speaking world. Telford went back to Scotland, his native Scotland, and over the next 20 years he built about 1,000 miles of road and 117 major bridges, most of them beautiful arch bridges like this, stone arches, but some essentially small models of his London Bridge. This one, Craig Gallachie, over the River Spey, Speyside. This is where the whiskey comes from. Beautiful bridges, elegant. He finally got his chance to build a great bridge in 1820 across the Strait of Menai, joining the island of Anglesey in northern Wales to the mainland. 500-foot span, and he built a suspension bridge, the first of the modern suspension bridges. In the background, we see a bridge built 30 years later by Robert Stephenson, the son of George Stephenson, the one who drove the first railway train, the Rocket. And that one behind is the railway bridge for this to get across the same crossing. And the belief was that suspension bridges couldn't carry trains, so they built a box girder which was supposed to have chains holding it up as well. Robert Stephenson took the contract to build that in 5 years, even though no previous wrought iron beam bridge had been built anything like this. And this project advanced structural engineering probably more than any other single project. It's called the Britannia Bridge. And here's the train going through that hollow box. Later in the railway age, this magnificent bridge north of Edinburgh was completed in about 1890. It was done by Benjamin Baker and John Fowler, and it had a span of 1,700 feet, which was about twice as long as any railway bridge built before. And again, the people responsible for approving the design had great hesitation about such a daring design. But luckily, Fowler was brilliant at explaining their ideas. And so this was the human model he made to explain how the Firth of Forth Bridge worked. And he said, when a load's put on the middle span, and that's actually Koichi Watanabe sitting on it, the first young Japanese engineer to come to the West to study railway engineering, the men's arms and the ropes will go into tension. So the men's arms here go into tension and the ropes over here. And the men's bodies and the sticks come into compression, the sticks and their bodies. And imagine the chairs 1/3 of a mile apart and the men's heads as high as the cross of St. Paul's, their arms represented by giant steel lattice girders, and the sticks by tubes 12 feet in diameter. And a very good notion of the structure is obtained, as indeed it is. When this bridge was completed, an American engineer speaking at the American Society of Civil Engineers meeting in Philadelphia in 1894 said, "The Firth of Forth Bridge is the clumsiest structure ever designed by man. An American would have taken that bridge and with the amount of money appropriated would have turned 50% of the money back to the owners." In other words, he's saying, I can do it for half the price. So when a Canadian bridge was planned to cross the St. Lawrence at Quebec City that had a span of 1,800 feet, just 100 feet more than the Firth of Forth, they didn't go to Baker and Fowler. They went to Cooper, the man who said, I can do it for half the price. And Cooper kept his word. He only had half as much steel as the Firth of Forth. Look how skinny these members look. And instead of using big 12-foot tubes, he used lattice work of members joined together. And unfortunately, they didn't work quite the way he'd assumed. And these members, under the push, buckled like this. And that buckling brought the bridge down like that. And 76 men died, if you can call a 14-year-old boy a man, who was the youngest who died. In the commission following that, our first dean, John Galbraith, was the technical expert, led the technical investigation, and placed most of the blame on Cooper. 2 Canadian engineers, Johnson and Duggan, then took over, founded the Dominion Bridge Company, and that company built the replacement bridge from 1910 to 1918. And when it was finished, it was the largest bridge in the world, 1,800 feet. It contained 2.5 times as much steel as Cooper's original design. At about that time, an engineer in San Francisco was thinking about building a bridge across the Golden Gate, and that required a span of 4,200 feet, and this was the longest bridge in the world, 1,800 feet. And he thought, I can do it. This was his first proposal. His name was Joseph Strauss. And this would technically have worked, but you must admit it's not elegant, right? It's safe, it's economical, but it's buck ugly, right? It's terrible. It was a combination of something like the Quebec Bridge and something like a suspension bridge. But he worked on it, and a few years later he involved a very elegant bridge, what has been called the Mona Lisa of bridges, the Golden Gate. Here it is under construction. It's a difficult thing to work out all of the loads that come on such a structure. An earthquake might happen, a ship might hit a pier, the wind will be high. How do you ensure the bridge is safe under all these conditions? Here is Strauss standing under the 700-foot tower, one of the towers of his bridge, Joseph Strauss. The tower isn't actually quite as big as it looks because Strauss was only 5 feet high and weighed 110 pounds. But he was unstoppable, and he is truly the father of this bridge. I gave you a definition of structural engineering at the start of the lecture. I'd like to give you a more honest definition now that you know a little about it. Structural engineering is the art of molding materials we do not really understand into shapes we cannot really analyze, so as to withstand forces we cannot really assess in such a way that the public does not really suspect. And that's really what it's about. It involves a lot of unknowns and a lot of judgment. It's not just a mechanical set of calculations. At about the time the fourth bridge was being finished, the Eiffel Tower was being built. And that tower used reinforced concrete as its foundation, a new material, steel combined with concrete. And a young man was doing classes at a great university, the Swiss Federal Institute of Technology, ETH, in Zurich. And his name was Robert Maillart, and his professor, Wilhelm Ritter, was one of the first professors to teach reinforced concrete. And Maillart became the greatest concrete designer of the 20th century. And this is his masterpiece, the Sauginer-Tobel Bridge in Switzerland. It's a little masterpiece. I mean, the Golden Gate Bridge cost $36 million at the time, which in today's terms would be $400 million. The Sauginer-Tobel Bridge cost 150,000 Swiss francs, which was probably about $50,000, not $36 million. The bridge joins two very small villages in the Swiss Alps. You can see one of the villages way up here. Here's the bridge down in the bottom left corner. It was only possible to service such tiny villages by building a very economical bridge. And this bridge, which spans 300 feet, 90 meters, goes across a gorge that's 90 meters deep. And here's the formwork they built to get across that gully so people could drive a car to the village. And here's Maillart standing there on the left, Robert Maillart, with Florian Prada, the contractor who built the bridge, and the local postman who now can go across the bridge instead of going down and up and delivering the mail to the village. So he's probably the happiest guy in the picture. At about that time, 1930, that's when Maillart's bridge was finished, a Frenchman called Eugene Freycinet, he came up with the idea of pre-stressing concrete before you load it, putting high-strength steel cables like Strauss used for the Golden Gate Bridge, and stretching them and clamping the concrete together so it could resist tension more effectively. Concrete and stone are very good if you squash them, but nowhere near as good if you pull them. This material revolutionized the way we use concrete. And we have a local example. This is a pre-stressed concrete structure, the CN Tower. It's still the tallest freestanding structure in the world at 1,815 feet. I'd like to finish by just talking a little bit about some pre-stressed concrete offshore structures that I've been lucky enough to be involved in. These are called condeeps, concrete deep water platforms. And here's one of these being towed out to sea. And I'd like to read you what a Norwegian woman, a poet, Gidski Andersen, on the Nobel Prize Committee for Literature, wrote. A huge reptile in the fine rain mist, the giant legs protruding out of the water with the platform towering above. It's a magnificent sight. And in these days when we hear that for the first time in hundreds of years, Norway may no longer have a merchant fleet or a seaman's trade, there is something hopeful about these exact and mighty platforms that sail out of our fjords. I don't know much about the mammon-influenced world of oil, but the engineering art displayed in these platforms truly impresses me. This is a poet talking about an oil platform, okay? And she's saying it's art. And that's because it's elegant and it touches her. And these structures really deserve to be compared to the Pantheon. They've really pushed the technology. And they've built many of them. And the deepest one goes 300 meters, so the Eiffel Tower would not quite make it out of the water there for the one on the right. But I want to talk about this little one in the middle there, the Schleipner platform. And when they put the top on, they sink these platforms almost right beneath the water, and then they float the top over them. And when they were doing that in Schleipner, one of the walls failed, and the platform was destroyed. And here's the cover of the Norwegian Engineering magazine, which says, "From an engineered cathedral to concrete scrap." It had taken them 3 years to build that. And there was a mistake, and it was destroyed in about 20 minutes. It was destroyed because of a shear failure, not a bending, but shear when you go like that. And we're not very good at designing for that. We happen to study it at the University of Toronto, and that's a shear failure of concrete you're seeing there. And so the Norwegian engineers came here to help, so we could help them solve their problem. And in just 18 months, they redesigned and rebuilt a replacement platform, and there it is in the North Sea. Last June, there was a huge gas pipeline joined to it from England. It's going to bring gas from Norway to England. These platforms are designed for the unknown forces that they may get in a huge storm. And we also have to design our structures for natural catastrophes like an earthquake. Here's one of the local technical magazines, you may have seen it, the Toronto Sun, describing the results of a Japanese earthquake. And we also have to worry about the impact of planes on our structures. And the structural engineer who designed the World Trade Center, Leslie Robinson, he worried about such things, so he designed his platforms for the impact of a plane. He thought maybe in a fog, an airplane looking to land, circling around, would hit his structure, so it was designed to resist that. He didn't think of an airplane going at full speed, hitting it. And of course, we know what happened. Here's Les Robertson. He was about 36 when he did this design. And here's what he said in an interview in October of 2001. The writer sitting in Robertson's conference room, which overlooks the World Trade site, said, "Your structures had saved a lot of people." And he said, "Yes, a lot of things worked well. People got out, and I suppose I'm proud of that." But he was looking towards that unavoidable view from the window. "It's a tremendous responsibility being an engineer," he said, his voice breaking. "It's a very imperfect process. It's not so beautiful as science." He struggled to keep his composure. "I have a lot of tough nights. I'm still not sleeping. I go to sleep for a little while, but I wake up thinking. I have so many thoughts." He put his hands over his eyes as though that would block out the thoughts. And after a minute he said, "There are all kinds of terrible things that take place on this planet that nature brings on us. But this event, Not only was it man against man, but it was live on television, and we watched it, and you could reach out and touch it, but there was nothing you could do. To finish on a slightly more hopeful note, here's the Hibernia platform off Newfoundland, designed to resist these monster icebergs. And here's the sort of wall that's designed around it to resist the impact of the iceberg. This is the wall that John Rennie, Telford's competitor who won the London Bridge design, used around his pier for the London Bridge. It's very similar. These two structures are essentially the same. Here's an ad from The Economist of a few years ago. At the top, this is the latest thing in microprocessors. In 12 months, it will be obsolete. This is a brick. In 12 months, it will still be the latest thing in bricks. This course is going to be about bricks. What we'll be teaching you will not go obsolete in the 50 years of your professional life. I end where I started, with one of these tough old Romans who ruled the world. This is Trajan, and Trajan's consul was Frontinus. And Frontinus said, amongst other things, that the maintenance of these works, these great civil works, is the most important part of the duties of this office, as it gives the best testimony to the greatness of the Roman Empire. Whoever is placed in charge of them should know which of them are in need of having money spent upon them. These numerous and extensive works have a natural tendency to fall into decay, and they must be attended to before they call for very large appropriations. Frontinus, in writing to a friend who'd suggested something about Frontinus's memorial when he died, Frontinus said, "I don't want one because remembrance will endure if the life has merited it." Think about what you're going to do in your professional career so that you will leave something worthwhile. In my field, we're lucky to deal with things that, if we do them well, will survive longer than us. This is the crest of your university. And that's a line from Horace, a contemporary of Augustus. Velet aber Ivo. Grow like a tree through the ages. Keep growing. And that's a good motto for a university. It doesn't mean keep getting fat. It means keep intellectually growing. Keep alive. So, good luck.